Hi, I'm Dr. Priyanka Chaudhary. In this video, I'm going to talk about electromagnetic wave spectrum. As an ophthalmologist, you should have a little bit idea about physics of electromagnetic wave spectrum. So why we should learn about electromagnetic wave spectrum? Because there are various machines, therapeutic machines, investigating machines which are used in ophthalmology, which are based on the properties of electromagnetic waves. Okay, so in this video, I'll be talking about electromagnetic wave spectrum. In the next video, I'm going to talk about harmful effects of electromagnetic waves on the human eye and various investigating and therapeutic machines used in ophthalmology based on the properties of electromagnetic waves. So what are electromagnetic waves? The electromagnetic wave, it is made up of two words, electric and magnetic. So the wave is made up of two waves, electric wave and magnetic wave. So these electric waves and magnetic waves, they travel in the same direction but perpendicular to each other. You can see here in red it's electric field, in red it is shown electric field, and in green it's a magnetic field. They are traveling perpendicular to each other but in the same direction. So how the electromagnetic waves are produced? Okay, so suppose there is a charge, it's a positive charge or a negative charge in a space, isolated charge. Each charge, positive or negative, it will have its own electric field, that is called a static electric field. Here it is shown the positive charge in the space, it's isolated one, and it has got its static electric field. This is the negative charge in a space, isolated negative charge in a space with its static electrical field. So when the negative charge comes in contact with a positive charge, as we know, they will have this attractive electric force. So there are different types of forces. In universe, there are forces which are repulsive and attractive. So there is electric field which can either push you or attract you depending upon the charge you have. So there are different types of forces in the universe. The forces which attract, the forces which repulse you. So these are contact and non-contact forces. So these electric forces. So electric force, it will either exert the repulsive force or attractive force. Similarly, the magnetic force either have the repulsive force or pulling force. It will either push you or attract towards it. Then another thing is nuclear force. It will only attract. Then there's a gravitational force. It will also only pull you towards it. So this is the electric field. This is positive charge, negative charge. When the negative charge comes in contact with the positive charge, it will experience that was about the attractive forces and repulsive forces. Now how the electromagnetic wave is produced from the electric charge, that is shown in this video. I have got this video, it's a beautiful video from the YouTube. I have given its link here, video title, so that you can search here, but I'll play it here to make my video complete and more comprehensive.
Light is commonly defined as an electromagnetic wave. But what is an electromagnetic wave? And also, what is electric and magnetic about light? To answer this question, we need to talk briefly about electric fields. But don't worry, it's going to be short. A charge placed at a given point in space will generate an electric field around it. The strength of that field at a given position is represented by a vector. The magnitude and the direction of this vector represent the magnitude and the direction of the force that would experience a positive charge of 1 coulomb placed at that position. Now, imagine a metallic bar and focus on one of the electrons in the bar. This electron creates an electric field around it. Then, connect the bar to a source of alternative current. The electron will move back and forth in the bar with the current. It will oscillate. And so will the direction of the electric field the electron generates. This idea is a key point. If you look at how the y component of the electric field strength vector changes with time, it is oscillating, and it can be represented by a beautiful cosine or sine curve. In the second part of the 19th century, Maxwell showed that a changing electric field generates a changing magnetic field and vice versa. So the oscillation of an electric field always generates a magnetic field that oscillates too. Let's go back to our electron. Suppose now that I choose for the alternative current a frequency of oscillation of 10 kHz. This means that the electron oscillates 10,000 times per second. And so does the electric field it generates, as well as the induced magnetic field. Imagine now that I place another metallic bar in the oscillating electric field. The electrons in this bar will feel an oscillating force. Yes, they are in an electric field, so they feel a force. They will start to oscillate too. What we did here is we transmitted a signal through space. This is how radio works. Yeah, we have two antennas. The first bar is emitting the signal. The second bar is receiving the signal. When the oscillating electromagnetic field is generated by the first bar, it propagates through space at the speed of light. Yeah, the oscillating electromagnetic field is what we refer as an electromagnetic wave or EM wave. And it is also more commonly referred as light. For example, let's increase the frequency of the alternative current up to 10 trillion Hertz. The electron in the bar will oscillate at 10 trillion Hertz, and so will the electric field it generates. The resultant EM wave is now infrared radiation. Let's increase the frequency a little more, up to 1 quadrillion Hertz. The metallic bar starts to glow now. It emits visible light.
Electromagnetic wave can be produced using a magnet also. When the magnet is moved through a coil, it will move its electrons that will produce the electricity, and hence the moving charges will again have the magnetic field around them, and this will give rise to electromagnetic field. The electromagnetic wave production using a magnet is called as electromagnetic wave induction. In this video, we'll see that.
Explain the atomic origin of magnetism. We know that certain materials behave like a magnet without any influence of external magnetic field. And certain materials behave like a magnet only when an external magnetic field is applied on them. So why is it that some materials behave as a permanent magnet, and some materials show the property of magnetism only when an external magnetic field is applied on them? To understand this, let's analyze the material at an atomic scale. We know that an atom consists of nucleus, surrounded by electrons that revolve around it. And the electrons and nucleus also rotate about their own axis. We also know that the flow of charge indicates the flow of current. And when a current flows through a circular coil, magnetic moment gets induced in the coil in the direction given by the right-hand thumb rule. Similarly, in an atom, the rotation of nucleus and the revolution and rotation of electrons indicates the flow of small currents in them. This flow of current induces magnetic moments. The resultant of all the magnetic moments gives the net magnetic moment of the atom. Now, if all the magnetic moments induced in the material are in the same direction, then the material behaves like a magnet without any application of external magnetic field. But if all the magnetic moments induced in the material are in different directions, then they cancel out each other and their resultant becomes zero. In such cases, the material does not behave like a magnet. To make such materials behave like a magnet, we need to apply some external magnetic field on them. Thus, we can say that atomic origin of magnetism in any magnetic material can be explained by taking into consideration the magnetic moments of the spinning and revolving electrons and also that of the spinning nucleus. Mathematically, magnetic moment due to the revolving electrons is given by magnetic moment due to the spinning electrons is given by, and the magnetic moment due to the spinning nucleus is given by, where the related term is.
This is a simple coil, and it has a very important role in designing many machines. When you connect the coil with a supply, it starts converting electric energy into magnetic field. Now let's take a different case. When a magnet is suddenly put near to the coil, an EMF rises at the ends of the coil. But this EMF will disappear as our magnet stops moving. If we pull magnet in opposite direction, EMF will also start producing in opposite direction. For producing EMF continuously, we have to keep our magnet moving. It is called electromagnetic induction. This phenomenon is used in countless applications.
Electromagnetic waves are of different types depending upon its wavelength, its frequency of vibration, and its energy. So this diagram is giving the electromagnetic wave spectrum ranging from the radio waves to the gamma rays. So radio waves having the longest wavelength, then comes microwaves, then infrared, then the visible light, then ultraviolet rays, X-rays and gamma rays. Radio waves having the longest wavelength and gamma rays having the shortest wavelength. And the visible light spectrum, it ranges from around 400 to 700 nanometer. So the light can be defined as the electromagnetic wave spectrum from the range of around 400 nanometer to 700 nanometer to which the human eye is sensitive, or the electromagnetic wave spectrum in this region that is visible to the normal human eye, that is called as a light. This picture is showing the electromagnetic wave spectrum with their wavelengths. So radio waves, as we have discussed, it has got the longest wavelength, that is more than 0.1 meter. Microwaves having it in the range of 0.001 to 0.1 meter. Infrared region can be divided into three types, A, B and C. The infrared C region is in the range of 3000 to 10,000 nanometer. Infrared B, it is in the range of 1400 to 3000 nanometer. And A, it falls in the range of 780 to 1400 nanometer. Visible light, it falls in the range of around 400 to 780 nanometers, that is 4 into 10 raised to minus 7 to 7 into 10 raised to minus 7 meters. So we know the mnemonic VBGYOR standing for violet, indigo, blue, green, yellow, orange and red. So violet, it falls in the range of 380 to 435 nanometers. Indigo falls between 435 to 500 nanometer. Blue is in the range of 500 to 520 nanometer. Green in the range of 520 to 565 nanometers. Yellow 565 to 590 nanometers, range from 590 to 625 nanometers, and red from 625 to 740 nanometers. Ultraviolet region, it falls in the range of 1 into 10 raised to minus 8 to 4 into 10 raised to minus 7 meters, and further it is divided into three regions: ultraviolet rays C, B and A, because it has got various effects on the human eye and human organs. So ultraviolet rays C, it falls in the range of 315 to 400 nanometer, B in the range of 280 to 315 nanometer, and ultraviolet rays type A, they fall in the range of 200 to 280 nanometers. X-rays fall in the range of 1 into 10 raised to minus 11 to 1 into 10 raised to minus 8 meter. Gamma rays, they fall in the range that is less than 1 into 10 raised to minus 11 meter. Then finally the highest energy waves are cosmic rays having the shortest wavelength. I said gamma rays earlier, but shortest wavelength are of cosmic rays. Okay, so again this diagram you can see here, these are the types of various electromagnetic waves. So this is the radio waves that is used to broadcast radio and television. Microwaves, these are used in cooking, radar, oven, telephone and other signals. And infrared waves, they come from the sun, fires, radiators. They can be used in the remote controls. Visible light, it is a range because of which our eye sense world exists. Ultraviolet rays, these are absorbed by the skin and these are used in fluorescent tubes. X-rays, these are used to view inside of the bodies and objects. Gamma rays are used in medicines for killing cancer cells. For radiotherapy, this is the chart showing various kinds of electromagnetic waves, their wavelength, frequency and energy. This chart I got from NASA website. This is the picture I got from NASA website. So this diagram showing different types of electromagnetic waves. Radio waves, we have seen these are used in radios, broadcasting, television shows, AM radios, FM radios. Then microwaves are used in microwave oven, cooking. Infrared region again can be used in remote controls. Then the human body, obviously the human body is made up of different neurons, various chemical reactions going on, various electric fields, potentials are being generated, so the movement of the electrons and charges all around the body, around firings in the brain, they are all emitting the electromagnetic waves in infrared region. This is the visible light from around 400 to 700 nanometer. Then these are the X-rays, then gamma rays, and then the cosmic rays.
This is entire electromagnetic spectrum. And this is the portion of the spectrum that we can see. But what if our human eyes were not so pathetic and we could see the entire electromagnetic spectrum? Yes, there is probably no evolutionary advantage to that, but still, what's wrong with imagining, right? What if we could see it all? Radio waves, microwaves, all them waves. Let's see what your vision will be like if you can see the entire spectrum. So let's start slow with complete blindness onto the full spectrum. You might have noticed that after expanding beyond our visual spectrum, we are representing the infrared waves and the ultraviolet waves using the colors that your brain can already process, which are some combinations of RGB, red, green, blue. If your current brain had to see the entire spectrum, then this is how it would see it, because it cannot process other electromagnetic waves. That's what the devices that help us see ultraviolet waves and infrared waves do, process the waves into the colors that our brains can already see. So seeing the entire spectrum will just become very overwhelming for your brain. One workaround can be eye having the ability to focus itself to different ranges in the spectrum, just like it can focus different distances, so it can see only a small range of electromagnetic waves at a time. Obviously, the other workaround would be to add more cones to the human eye, which could help us detect more colors and simultaneously increase the ability of the human brain to process all those new colors. But frankly speaking, I don't have much hope for the human brain. Our brain is programmed to work in the most energy efficient way and not necessarily perceive the reality as it is. And perceiving the entire electromagnetic wave spectrum is not necessary for our survival at all. So our perception is restricted to a very small range of reality. Just imagine what else is out there beyond our perception that our brain doesn't even get a whiff of, and we just assume that we are experiencing the true reality.
This video I have really liked because it stimulated my scientific imagination. What if I could see the entire electromagnetic spectrum and voluntarily focus on a particular wavelength form whenever I wanted? Then I could see if there is anyone beyond the closed doors or solid walls inside the house and what people were doing. I could see human bodies behind their clothes, their bones in X-ray range using radioactive isotopes. I could detect malignant and dysfunctioning non-functioning cells in gamma range. With cosmic rays, I could see the electrons, protons, neutrons, atoms, molecules functioning together, making a human body. And who knows, I would be able to see even ghosts and souls if they fall in any of this electromagnetic wave spectrum, invisible to the human eye. Because energy can neither be created nor be destroyed, but converted from one form to other form. And in spirituality, in Buddhism, they say mind and matter, nothing but mere wavelets interacting with each other. Who knows when on the death of human or any being, its energy may be converted to mechanical wave traveling along the air as ultrasonic wave or beyond the perception of human ear and confined to earth as mechanical waves cannot travel through vacuum space. Or maybe after the death, the energy takes the form of any of these electromagnetic waves and can travel beyond Earth's air atmosphere and into the space and can land on other planets. Who knows? I really loved imagining this scientific stuff. Let's see another video I liked on YouTube about the light.
Hey, it's Professor Dave. Let's learn about light.
He knows a lot about the science stuff. Professor Dave explains.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation.